All right, thank you for joining. This is the last session. Hopefully it'll be interesting and worth your time. So what I'm going to talk about is the remote monitoring application, not only monitoring monitoring the scientific instrument, but also able to control it to some extent. Let's get started with that. Slight background, I've been working at Thermo Fisher for quite some time now. I'm a cloud architect there within the platform research and development group for life sciences. You can reach me at that email. At a high level, what I'm going to talk about today, we'll get to Redis. I'll talk about the connected ecosystem on Thermo Fisher. What are the different ways we connect? Why did we even build this application? So I'll talk a little about the customer needs. Then how did we actually get to the final architecture of this application? So I'll go through slightly through the different design iterations, different infrastructure pieces we picked, and eventually we got to where we are with Redis. We'll talk a little bit about the cache storage internals in terms of what tricks we have done, what features we've used, and so forth. And finally, we'll end with the final architecture and some key takeaways for you. So again, we're talking about one instrument specifically here. This is a DNA sequencer. So if you have to get your DNA sequenced, future of targeted medication and so forth, you would be having something like that. There's the next generation sequencing devices, which are much higher throughput, but the capillary electrophoresis devices are the gold standard. So what we do is we have this sort of connected ecosystem. On the left side, you see that's our instrument. It's connected to Thermo Fisher Cloud. We have applications where you can define your run protocols, how your instrument's going to work. We have applications that let you monitor the runs. We have native mobile applications. We have cloud applications. And then when the data gets generated by the device, there's primary analysis that happens on the device itself, and then the result files are shipped to the cloud. And we have a bunch of applications for secondary analysis. You have the ability to share these results within teams, across groups, and so forth. So customer needs, right? Pretty much when we want to build an application, why did we build this application? So users or our customers were really interested in monitoring these runs remotely. They wanted to see where we are at when a run is going on. Some of these runs with longer run protocols can take fairly long. This can take about 8 hours, 10 hours. So you don't want to be watching the instrument, right? So that's one purpose. There's some sort of real-time quality control. These devices have in-run QC. So based on as the run is happening, we'll start throwing certain flags that maybe your data quality is not coming right. Maybe you didn't set up the right chemistry, or the protocol is missing. So you get that kind of real-time feedback. And you get that feedback, then what do you do with that feedback? Maybe you want to stop the run, or you want to pause that instrument and go take a look. So you could do that. So that's the control aspect of it. So I'll talk about the whole architecture. Since this is Redis, this is the data store. Whenever you're working on an application, the key aspects to look at is you're going to figure out that this is where my data is going to reside. I think these are key attributes. To start with, you should look at what the data structure is going to be. Is it going to be really a SQL database, a NoSQL database, right? This is JSON data you're going to be working with. What are your access patterns? Access patterns are fundamental, right? Access patterns will define whether you need to do, for example, if you put your data, NoSQL database in S3, and your user interface needs performance at millisecond level, how do you attain that? In order to attain that, maybe you'll create some sort of indexing, and you'll store that index in some sort of cache cluster, right, to give you that sort of performance. That ties with your data access characteristics, right? Is the data sitting in a hot system? Is it warm or it's really cold? Right? Is it in a cache? Is it sitting in maybe in a key value store like S3, or it's maybe somewhere else, right? Cost. You can build a system. I'll talk a little bit about it. You can do a lot of prototyping and you can come up with a perfect design. And when you do some sort of load test and you say, you know what, in order to scale to this concurrency, this is how much it's going to cost. And all of a sudden your product management comes back and say, no, we're not willing to pay that much, right? So cost should be a fundamental thing when you're trying to design a system end to end. Keep that in mind. So I'm going to talk about few design iterations. So we had those requirements. We wanted to build a remote monitoring system, and we wanted the ability to be somewhat instantaneous. So thought, okay, so we said, you know what, a little bit the data that's coming. So we are an AWS shop. So I'm going to talk a lot about AWS infrastructure pieces here. When our device gets connected to AWS, we publish messages through IoT. So those messages, most of that data is coming in JSON structure. And as the data comes, maybe this is one design iteration, right? I would put a fire hose. The data will come to fire hose. I'll have some sort of rules, and then I'll say my final store is Redshift in this case. S3 is there because it could be your intermediate store. Or you could, there's an option you could have it, not only for failure conditions, but maybe you want to process these files later on, so you would put them in S3. I have two things here underlying. One shows you how things go through Firehose. So you have a Firehose delivery system. When we started with this design, there were no capabilities to do transformations, right? So you could use some sort of JSON path and extract some data and then put it in a store. But lambdas, for example, were not there. So I could not transform the data. I could collect the data and then store it. But the transformation, now they've added that. I think, I'm not sure when it was added, but it's been there. So you could do some level of transformation as well. So you could say, I'm collecting the data, I'm going to transform. I can specify maybe lambda as my compute capacity that can do that kind of transformation. And then eventually I can say that, you know what, this data will reside in my Redshift, which is sort of a data warehouse system. So we have taken an NoSQL data, put it in a data warehouse. Now I can do magic. Since it's SQL, you know, Redshift is, I'm not going to get too much into the detail, but Redshift, you can think of Amazon's version over Postgres. They use a lot of optimizations on top of that for scale, for performance, and so forth. And there's another thing on this slide is the rule engine, right? So this is what decides how, when the data comes on a certain topic, where it gets navigated to. So as I was talking about, so you have the ability to do JSON Pats. So you can look at the data in the JSON format and then store it inside Redshift. You could do as is, right? Maybe you could write some sort of ML capacity on top of your Redshift. The cost model really here is you pay for Firehose, you pay for S3, you're paying for storage as well as put IOPS, right? Every time you do a write on S3, you incur a cost. Redshift cost is associated with the instance type. So it depends on how many instances you have, and what the type of the instance will decide the cost. Okay, so how do we test this? The instrument wasn't available, and we wanted to come up with a design, right? So the first iteration would be that KPL. So KPL is like a Kinesis producer library, and there's a consumer library. So we wrote some code using these libraries, and we said, from Firehose, let's put it into Redshift, a small size, right? Just one shard of Kinesis and a very small Redshift instance. We're doing something like this. This is the kind of the data. This is typically our telemetry data. We have different forms of data. I'm just going to talk about this. So you have some sort of voltages coming out of the instrument. You have some sort of temperatures. This helps you troubleshoot if something is off on the instrument. So with Redshift, we saw, okay, we could put 50,000 records in there. We'll get about 3 seconds. So second level performance, right? Ingestion from S3 Redshift, pretty fast. That ingestion is happening, but the querying part is about this. Okay, so great. And these were some key metrics we were looking at, towards the end when we finalized something. Is our ingestion piece running all the time? Because the instruments are geo-distributed, the concurrency rate may differ. I don't want an ingestion pipeline running all the time without nothing coming in, right? So, okay, Firehose, there's nothing running all the time. Is it scale on demand? Yes, AWS will scale. You can change the number of shards and so forth. Does it decouple the persistence from the data that's coming in to as it's consumed by the applications? That could be your mobile remote monitoring app, that could be your web app or some other app. Yes, it does decouple. When we started, yes, the data is tied to the IoT message. So whatever you're generating on the device is what's being sent to you, and then you could do some level of extractions. Now, remember, they have introduced this Lambda piece, so you could do some level of transformations now. The performance of the queries, it's seconds, right? And the other thing, this is monitoring data. Do we really want to store everything in Redshift, or maybe there's an opportunity to learn? So I marked it as red here. Okay, that's our second design iteration. So we said, okay, why not put Kinesis in there, right? So we have Kinesis streams, and then we have Lambdas, and eventually let's put the data into Redis. Sounds interesting. Again, the same advantages we get. We're not running the capacity all the time, and then we can do a whole bunch of transformations. And the performance will be much better. And let's keep the Firehose pathway alive as well. So now we could segregate our data, right? There's some sort of ML things we want to run, some sort of predictions we want to run. Maybe we'll do that on our Firehose-based pipeline. And there is something we want the customers to get real-time feedback. Like if something is going on the instrument, if there's an error condition, I want them to know right away. If they want to pause or run, I want them to know right away. So that kind of data, let's funnel it through Kinesis and directly into Redis. Another design thing we were thinking was that maybe let's use SQS for events, and let's put everything else through Kinesis. But then eventually we realized, we don't need that another piece. We can route everything that's important, needs realistic real-time performance through Kinesis, and everything we want to run ML and things like that through the Firehose. So this was our design iteration 2. Again, same thing. We didn't have the instrument ready at that time, right? So the instrument development team is working on the instrument. We have some contracts established that this is how the data is going to come in. So we did our second sort of prototyping. We said, okay, we're going to again use the KPL and KCL libraries to produce and consume the data. And now instead of storing everything inside Redshift, we're going to use Redis. Again, this is a small node. We're just trying to play with it and see what we get. This is running behind a VPC, so we're using some sort of port forwarding. Okay, this is interesting. So we have 5 instruments. We store about 25 runs for that, about 53K events, about 1.3 million, about 920. So we have about 41 runs, 1 gigabyte, about 2.2. This is our test case to see, how Redis is going to perform. And Redis performs amazingly well, right? So from seconds, we're down to milliseconds. Again, this is not one thing to keep in mind, right? The baseline here is not the transfer time, the latency, everything. This is purely evaluating your backend, purely comparing this against Redshift, whether Redshift is okay for everything, or maybe for our real-time performance data, we want to switch that from Redshift to Redis. So we were happy with it. And by segregating the data, we don't really need to have a super large Redis cluster either, because we saw that, for over 2 million events, the kind of memory consumption is only 1 gigabyte. Well, that's amazing. Okay, so that takes us to this. So we say, okay, we've decided what we're going to do. Now our data format is no more tied to IoT message. We have a Lambda in between, and we can actually transform the messages to a format that can be easily consumed by our consumer, our application. Maybe we'll have the similar format. our performance on the queries is much better, right? From seconds, we're down to milliseconds. And we don't need to store this data all the time. So when the run is done, when the new run needs to happen, get rid of all this data. This data has no value to us. The real value is the metrics or that kind of data which we have collected and pushed it in our Redshift cluster. Right? This data is for real-time monitoring only. So this is similar to like trying to tie it to the decoupled sort of data bus. Your device is producing the data goes to the IoT gateway. We have some sort of rule engine there. From that rule engine, it decides if the data is coming here, we'll push it to Kinesis. From Kinesis, we take that and eventually put it in S3 from the Lambdas and into Redis and so forth. The interesting things here is that with Kinesis, you have ability to run multiple applications. You can do sort of the time window sort of thing. You can even increase the amount of time the data resides in Kinesis. You can have the data sit there 1 day for 7 days, based on your needs, and then until and unless I've acknowledged it, your data is there. Event ordering. So event ordering, it guarantees that you get the order, but we still use sorted sets inside Redis with timestamp, source timestamp as a score, and it's a managed service. Okay, so at high level, what do we have? We have a cloud web application. This is based off of EC2. Again, this is the part that consumes the data and shows it inside your browser. We have an application that is responsible for ingesting the data. That's your Lambda processor. And then we have an event repository, right? So eventually some data will sit in Redis, everything that's real time. Some of our analyzed files will go to S3, and then we'll have some data we want to do some sort of ML or some sort of dashboarding using Jasper or anything that'll be inside Redshift. Device Connect is another one of our internal applications that shows, what's the state of your instrument and so forth. Okay, so this is what we have. This is sort of a repeat slide, but this sort of conveys the message, this is how our architecture looks like. Your data comes to the IoT, it's streamed, we put it in Kinesis stream. We have multiple streams there. We have different streams for experiment data. We have different streams for events. There's different streams for matrix and so forth. And there's lambdas that, again, with the streams, you can specify that once you've collected maybe 1,000 events or 1,500 events, trigger this guy, right? So Lambda comes along, picks those things, does some sort of transformation, and shoves the data into Redis. Similarly for Firehose, some of our metrics data goes from Firehose and sits inside Redshift. We have applications, Jasper dashboards and things like that you can run and see what's going on. This is our customer-facing application that consumes the data. This is the web application. It's using an EC2 cluster. It's not using a stack of Lambdas. We'll talk about a little bit about that towards the end, why we did EC2s. Okay, you saw the remote monitoring part, right? How does the control happen? We are an AWS shop, so this is how control happens. I told you there's an application called Device Connect. So Device Connect is really responsible and gives us REST-based APIs if from within the customer-facing application you want to do some remote commands on the instrument. Let's say you saw the data that's coming in and you see there are some issues. There's some sort of diablobs or anything on your raw data, and you want to pause that run. So what will happen is you'll call pause, and that pause will invoke a REST API on our another internal application called Device Connect. What Device Connect internally does is it'll update the shadow for that particular device. Again, it's an AWS concept. And then there's a piece on the instrument that's listening on the Delta topic for that shadow. As the update comes, we receive that, and then we either accept it, reject it, and then we send our confirmation back to the Device Connect. And the customer application gets the result by querying that command execution ID, whether that remote command succeeded or failed. That's how we are able to communicate back to our devices. Okay, about the cache storage. We're using Elastic Cache. It's a managed service from AWS. High availability is achieved out of the box. I mean, we're running multiple availability zones. We run read replicas. It's a Java application. Spring Data is what we use. JRedis is the connector. You could use Redis, but that's what we ended up using. Spring Data itself is cluster aware. So a couple of points here. I'm not doing any sort of hashtagging here. So what we ended up doing was we used cluster mode disabled. So we're not using cluster mode enabled. So we are essentially one shard. And the way we can scale this is vertically, right? So we have read replicas around it, which will automatically take over in case of failures and AWS will promote that to a primary, one of them. So that is there. One of the biggest reasons why we didn't do that was the performance. So we use pipelining extensively. That gives us much better performance compared to singular inserts into Redis. So with that pipelining, at least the version we used, both for the Redis engine version, the Spring Redis, all that combined together, the optimal was to use a single shard, let it scale vertically, and then we get much better performance. We use a lot of ordered set. All the experiment data that comes, we push them into ordered set. The score is the timestamp, the source timestamp. Redis PubSub is also used. I'll talk about that a little bit later. And we use again, there's another repository sort of implementation that's available from Spring for our metadata and so forth. How do we manage the memory, right? So as I said, this is not something we want to hang on to. Once the run is finished, you've monitored that run, you've looked the results are good or not, you move on, and you eventually want to clear that out. How do we take care of that? Okay, we thought of using Lua scripts, and then we read around and said that maybe there'll be some sort of performance issues with it. We don't want to do that, so we shied away from Lua scripts. I hear a lot of people are doing amazing things with Lua, but we did not do that. We use a volatile LRU, standard setting for Redis. And then remember the remote commands. So when an instrument, essentially this doesn't use the remote command, but at the end of the run, we send something called this plate remove event from the device. As that device event comes to us, based on that device ID, we remove everything in Redis for that. In some cases, that event may never come, right? So we also run a cron every night to figure out, based on the metadata. So every time a run happens, we store some metadata around that run. So every night our cron will pick up and say, okay, these guys are older than 1 day, I'm going to evict them. So we delete all of those things. And ultimately, we put a TTL of 3 days on everything because we don't want our memory to build up. So any key that goes into our system has a TTL. That's how we manage our memory, right? So we've tested it, there's no buildup, and we've tested for certain concurrency, right? And beyond that, we'll have to scale and things like that. I'm sorry? Okay.
Your TTL is set to 3 days.
Yes. Yes. Yes.
How can you find something that's older than 7 days?
Yeah, so I think, that's, I should have put a cross next to it. We didn't do that. Yeah, okay. So basically she's saying that, there's server-side scripts removing entries older than 7 days. How can you find anything there? So that we never implemented. That was the Lua script-based implementation. We didn't want to go that route. The first line. Yeah. Yeah, so that's not implemented. We never put that. That was one thing we thought, we'll do it that way. But again, based on different blogs and so forth, we shied away from it. And instead, what we did were 3 things. One thing was that every time the run finishes, the instrument sends a plate remove event to clean up data related to that device ID. Some cases that event may not come because you need to navigate to a certain place in the instrument. If you don't, that event doesn't come. So the second thing we do is that we run a cron based on the metadata. And ultimately, if even there's some failure in that cron condition, ultimately we put a TTL on the events. So it's like fail-safe over fail-safe to make sure there's no buildup. Right? So we don't want any buildup happening on this cluster. So the performance and reliability. So we did few tricks here. So the ingestion is happening all the time, right? When the run starts, you don't have to connect to a remote monitoring application for the ingestion to happen. As the run starts, the instrument starts sending data, and we start storing it. Well, the client application can start monitoring in the middle, right? So there's already something happened, and you go back to your desk maybe 2 hours later, and you start monitoring it. In that case, what our UI will do is it's not going to fetch at the same rate. It's not going to fetch basically this much data and then this much data. It can batch things together. So we have different APIs, and the first API call would be, give me everything you have for this run. That's much more efficient than having to query Redis over and over again when we can get a batch of data. What happens if certain key events are missing? We need certain things in our user interface to formulate what the different injections are. What if one of them is missing? And the other key thing here is that there are limitations on the IoT pipeline using MQTT. What's your message size? Right? So you have to be within those bounds. For some of our messages, they are big, right? And we can't send them as just a singular message. So we break them out, and we write an envelope saying that, you know what, expect this, and it's going to be broken down into these many messages, and the server side is supposed to put them together. What if, something never makes down? So for those kind of things, we use TTL. We inject certain keys into Redis with a very short span, say a second or 2 seconds. And when that key expires, we listen to that. Again, this is where PubSub comes again. So we listen to those expired keys and see whether that's of type re-request injection modules. Once we get that, then we send a remote command saying, instrument, can you send me this data again? Because I'm having a hard time assembling it together. Right? So that's how we deal with key events. So you have something missing, we figure it out, we send a remote command back to the device, and the device sends us, and we're all good. Again, I talked about a little bit about the configurable batch sizing. This is what I talked about, a little bit alluded to it when I said that, why our customer-facing application is not a Lambda or a stack of Lambdas, right? We internally run something called as a compute cluster. But if you look at the reds and greens, you'll figure it out. The green wins at the bottom on the right side. It's the consistent query response time. Lambdas have this cold start issue. You can solve some of those different ways by running some sort of ping that, whatever the container underneath that's serving the Lambda doesn't get recycled away, and then you basically have to respin the container and start serving. That has some lag time, right? Some few seconds. So it's not going to be consistent. And if you don't have a very high concurrency, that means eventually those containers will be recycled and you'll have cold starts, right? You cannot guarantee a consistent performance. So for those reasons, we decided, for our customer-facing applications, we want to put a compute cluster instead of relying on Lambdas. And none of our applications do that in production either. So, we shied away from taking risks. Last slide. Customers are very happy. So these are comments from some of our customers. She says, cloud is very convenient. Cloud, we can monitor the run from everywhere. They love our mobile app. They say, it's accessible on phone via the app. Amazing. It's a great feature. I think, so we're happy with the product. Customers are happy with the product. And with that, we conclude. Questions?
You mentioned you're using the pipeline to improve the performance, and also your Java application. What is the pipeline library you're using, or you're using Redis directly?
Oh, the pipeline.
Spring data,
Yeah. So it's the pipeline. It's another API call within the Redis template function. So you can pipeline if you know that. The thing with that is that your client doesn't have to wait for a response from Redis every time an insert happens. So you can batch. In our case, you need to make sure that you need to do some level of load testing and fine-tune that right number for you, that how many operations you want to batch for a certain type, and then you can run it through the pipeline.
And
there's nothing custom we wrote. It's just Spring Data API supported and provided via Redis templates.
Okay, and also you mentioned when you switch from Redshift to the Redis, the query performs much better.
Yes.
So how many index you have in your Redis? How do you query your monitoring data?
How many queries?
Yeah, how many different query criteria you're using here? Is it a simple query? Do you do any grouping, aggregation?
Yeah, so the real-time data is all sorted sets. So essentially, the data is sorted by score being the timestamp of the source. So we use a lot of rev range, that kind of APIs on sorted set, on zset ops. Yeah, and then the metadata I talked about, those are, it's Redis sort of repository. It sort of gives you that implementation underneath. And those are simple, like find this by this, or set this by that. So those are the main design principles within this application. And PubSub we also use for other things. So the analyzed files we get on the instrument, for performance reasons, we don't pull everything from S3 all the time. So once you pull something from S3, we'll try to cache it locally on our compute instances. And then when a plate remove event comes or the cron runs at night, we send a message saying that this needs to be deleted. So we delete that temp storage at that time as well. So that's another application for PubSub. So you have multiple instances on the compute, and they all can store these files temporarily. So that helps us serve the customer much faster. But then we don't want the disk to build up. For that, we use PubSub.
So you mentioned the cron
Yeah.
multiple times. Is that the same cron to clean up those
It's
files?
the same cron.
That's running on for the S3, right?
Yes. So S3 is two things. S3 you can even design or even define you can configure saying that the data should be ejected or deleted at this rate. You don't want to hold anything beyond a day or something, you can do that. The other thing from UI also, we use PouchDB on our UI. So if client has fetched some data, they don't need to fetch that again. We store it locally.
Do you have any server-side Redis script running on your application?
Server-side?
Yes. The Lua app scripts
No.
for Redis.
No Lua scripts.
Any other scripts on
No
the
scripts at all.
Redis server side?
Nope.
Okay.
It's
thank
just
you.
out of the box. Yeah.
So you mentioned the sorted set usage. Seems like you're usually getting the top, excuse me, the top sorted by timestamp, right? And occasionally you might need to get the entire sorted set. Do you see the new streams feature as being beneficial for you in improving the performance?
I don't know when we'll get to it. I mean, we are on AWS and we are miles behind, I guess. If AWS implements something like that, for sure. Yeah, it'll be interesting to look. There's a lot of pull happening here. Another thing we want to look at is probably maybe sockets and things like that. Rather than pull, do some sort of pushes. That will be another thing we want to look at.
Thanks.
All right. Thank you so much. Thank you.